The conservation of architectural heritage is an important goal, and more the subject of scientific research. In particular, we were interested in the effects of climate change on historical monuments, such as large Gothic cathedrals. Extreme windstorms strike our regions with increasing intensity and frequency due to climate change. The assessment of wind effects on this type of buildings, with large dimensions and complex geometry, nowadays can essentially be performed via experimental studies. The collaboration between the University of Florence, equipped with an experimental research facility on building aerodynamics, the ENSAM of Bordeaux and the University of Versailles led to a research work never done before: the determination of the wind pressure field on a Gothic cathedral, namely Notre Dame of Paris. This is a crucial step to assess the structural safety of the cathedral, weakened by the fire of April 15th, 2019.
Behind me, you can see the Cresceva Wind Tunnel, which was the first boundary layer wind tunnel in Italy when it was opened in 1994. It is a facility very different from the ones we are more used to, namely the classical automotive or aeronautical wind tunnels. Indeed, there is a long test chamber which is necessary to reproduce the physical characteristics of the wind in the lower layers of the atmosphere, both in terms of mean wind velocity profile with the height and in terms of velocity fluctuations over time. This is the purpose of the roughness elements that cover the wind tunnel floor, together with the other devices placed at the entrance of the test chamber. A fundamental step in the design of an experiment, like the one on the Cathedral of Notre Dame of Paris, is the determination of the geometric scale of the model. This choice must comply with the characteristics of the flow that we can reproduce in the wind tunnel. In the present case, we opted for a 1:200 scale. Another crucial passage is the choice of the measuring points on the external surface of the model, where the pressure taps will be realized and then connected to the pressure sensors. This phase is very delicate because it influences the internal structure of the model and therefore its fabrication. At this stage, the experience of the experimentalist comes into play, as one must envisage the pressure field on the structure in order to place the pressure taps in a suitable way for an accurate reconstruction of this pressure field after the tests.
The starting point of the work leading to the 3D printing of the Notre Dame model at the scale 1:200 was an existing numerical model of the cathedral. The work was divided into two consecutive phases. In the first phase, the main goal was the modification of the numerical model to meet three needs: the reduction of wall thickness to allow the installation of the pressure taps and the shortening of the printing time, the creation of 3D paths inside the model walls, guiding from the inside the passage of pressure tubes up to the external surface of the model, where the pressures are actually measured, the division of the cathedral in sub-models, allowing for the installation of the pressure taps. Once the coordinates of the pressure taps on the external surface of the model have been defined, the generation of the holes and the associated paths inside the model walls, note that we are talking about more than 1,200 pressure taps to be installed, was automized as much as possible by means of Python scripts interfaced to the 3D modeling software Blender. In the second phase, the target was the setting of the 3D printing parameters to find a compromise between the quality of the external surface of the model and the required printing time. Given the model dimensions and the required surface quality for the wind tunnel tests, we chose the 3D printing technique by fused filament deposition. The model production was attained with a Linkster 3D printer, selected based on the large dimensions of the fabrication pane and its excellent printing features. In addition, some parts of the model, in particular the spire, which required a greater attention to the details, were realized through stereolithography. Finally, the printing phase of the 13 portions of the model required about 2 weeks.
Once the various parts of the cathedral model are in the laboratory, it's necessary to start with the equipping phase. But what does it mean? It means connecting the small holes on the model surface to these Teflon tubes, connected in turn to miniaturized sensors incorporated in the so-called pressure scanners. Such a pneumatic connection is specifically conceived so that the pressure fluctuations that are recorded over time by the sensors are practically the same as those occurring on the model surface. In this way, we register 500 samples per second of the pressure acting in more than 1,200 points on the external surface of the model of the cathedral. The large number of pressure taps and tubes makes this stage of the work very complicated. Afterwards, we're ready to start the measurements. The model is mounted in the test chamber on a turning table used to simulate all the possible wind directions. We carried out 2 different sets of measurements. First, we placed around the cathedral model some diffused roughness elements in order to reproduce a generic urban wind profile. Then the tests were repeated, adding the model of the buildings that surround the cathedral and reproducing the 2 arms of the Seine River. To inspect the wind flow field around the cathedral, we can resort to visualization techniques using a smoke generator, as you can see in the video.
Once the pressures on the model surface have been recorded, the data are interpolated to produce maps of the pressure on the external surface of the structure. The movie clearly shows that the pressure field acting on the structure is definitely dynamic. That is, the pressures exhibit large variations in time. However, as a first step, we can study the mean pressure field and the distribution of the maximum and minimum values of pressures on the external surface of the model. It is clearly possible to see how these are dependent on the wind direction. Finally, after a comparison with the few works available in the literature for this type of buildings, we can conclude that experimental tests in the wind tunnel are absolutely necessary for an accurate assessment of the wind loads on such a complex structure.
This study, carried out thanks to experimental equipment at the University of Florence, shows the importance of scientific research applied to the conservation of cultural heritage. This is everyone's duty, not only of scientists, because the architectural heritage belongs to all of us.